What is the universe made of? This is a question that humans have been asking since we first looked up into the night sky. The universe is thought to consist of three types of substance: regular matter, dark matter, and dark energy. Regular matter consists of the atoms that make up stars, planets, human beings, and every other visible object in the universe.
We look in the universe and we see the effects of gravity, and let's add up all the stars and galaxies and planets and comets and black holes, everything we know about, to account for this gravity that we see. And when you add in the dark matter, this extra gravity, it turns the universe into the universe that we see. That's why we know the dark matter is real. We don't know what it is, but we know it's there because we can't make the universe as we see it unless we put this extra gravity into our simulations to match the gravity that we see.
In the last 6 decades, NASA, along with its international partners and thousands of researchers, have expanded our knowledge of the universe by using a full fleet of telescopes and satellites. They have been exploring the evolution of the universe from the Big Bang to the present.
The cosmic microwave background, a record of the earliest moments of the Big Bang. Then it takes a little time to make your first stars. We call it the Dark Ages. Stars are made, galaxies mature. We come up to the present day, 13.7 billion years later, and that telescope, Wilkinson Microwave Anisotropy Probe, made this measurement. And so it's a pretty coherent picture of the earliest moments of the universe.
The Wilkinson Microwave Anisotropy Probe satellite returned data that allowed astronomers to precisely assess the age of the universe to be 13.77 billion years old, and to determine that atoms make up only 4.6% of the universe, with the remainder being dark matter and dark energy. For the first 150 million years after the Big Bang, there were no galaxies or stars or planets. As time passed, the first stars formed. Stars collected into galaxies. Galaxies began to cluster together. Clumps of matter smashed into each other, and the planets in our solar system began to form around the sun. Our solar system, galaxies, and clusters of galaxies are all held together by gravity. However, something just doesn't add up. Galaxies seem to be achieving an impossible feat. They are rotating with such speed that the gravity generated by their observable matter could not possibly hold them together. They should have torn themselves apart long ago. The same is true of galaxies and clusters, which leads scientists to believe that something we cannot see is at work.
Particle physicists are convinced that it might be an exotic particle that doesn't interact with us, doesn't interact with our light, with our telescopes, but that it has gravity. So these particles are doing their own thing, invisible to us, but otherwise attracting our matter into nucleating us among them.
This mysterious substance, called dark matter, makes up the bulk of a galaxy's mass and forms the foundation of our universe's large-scale structure. Because dark matter does not emit, absorb, or reflect light, its presence is only known through its gravitational pull on visible matter in space.
It may be that the dark matter is not matter at all. It's the gravity from ordinary matter from a nearby other universe in the multiverse, whose gravitational influence we feel. And here we are, saying, ooh, we have a mysterious gravity, call it dark matter. Really, it's just ordinary matter doing its thing in an adjacent universe. We don't have data for this, but we have good theoretical and philosophical reasons to think that a multiverse exists.
NASA telescopes have helped us better understand this mysterious invisible matter that is 5 times the mass of regular matter. The first direct detection of dark matter was made in 2007 through observations of the bullet cluster of galaxies by the Chandra X-ray telescope. Another strange thing happening in the universe has been spotted by the Hubble Space Telescope. The observations of very distant supernovae showed that, a long time ago, the universe was actually expanding more slowly than it is today. However, the expansion of the universe has not been slowing due to gravity, as everyone thought. It has been accelerating. No one expected this. No one knew how to explain it. But something was causing it.
Some mysterious pressure in the vacuum of space acting opposite the force of gravity. Whatever it is, we call it dark energy. That's our placeholder term to describe what we observe. The acceleration of the universe. Nothing known will stop this. So there's been some concern that maybe space does not have the flexibility necessary to allow such rapid expansion. And might space care in some way previously unimagined? And what does that even mean? Does the question even have validity?
Scientists still don't know what the correct explanation is. This energy, in whatever form, is needed to reconcile the measured geometry of space with the total amount of matter in the universe. It turns out that roughly 68% of the universe is dark energy. Dark matter makes up about 27%. The rest, everything on Earth, everything observed with all of our instruments, all normal matter, adds up to less than 5% of the universe. The universe is far from being fully understood. There are many different theories as to what dark matter and dark energy actually are, but scientists have been searching for these elusive entities for decades. Recently, new methods of detecting these entities have been developed, which could lead to a significant breakthrough in our understanding of the universe. So, how do scientists even begin to detect what they can't see?
In science, in astrophysics in particular, you have the capacity to measure something, even if you don't know what it is. For example, you could measure the fact that something is falling to the ground, but not know what it is or what's causing it or why. But you can measure it. You can measure the sun moving across the sky, build calendars based on that, and not even know that Earth goes around the sun. You can make all manner of measurements and not know what's causing it. We measure this thing we're calling dark matter. We measure this phenomenon, dark energy, that's forcing the universe to accelerate.
Rebecca Liang is an astroparticle physicist at the SLAC National Accelerator Laboratory at Stanford University. She believes that Jupiter is an ideal candidate for detecting dark matter. Jupiter has a large surface area compared to other solar system planets. It can capture more incoming particles than any other solar system object. Liang has been working on detecting dark matter for years. In April of 2021, she presented the first dedicated gamma-ray analysis of Jupiter using 12 years of data from the Fermi telescope, which showed evidence for the first time of an astrophysical source of gamma rays. However, she found no signs of dark matter. In the continuing search for dark matter in our universe, scientists believe to have found a unique way to use exoplanets as powerful detectors. According to Yuri Smirnov, a particle theorist at Ohio State University, one of the best parts of using exoplanets as dark matter detectors is that it doesn't require any new types of instruments such as telescopes, or searches that aren't already being done. When the gravity of exoplanets captures dark matter, the dark matter travels to the planetary core, where it annihilates and releases its energy as heat. The more dark matter that is captured, the more it should heat up the exoplanet. This heating could be measured by NASA's James Webb Space Telescope. In 2025, NASA is planning to launch the Roman Space Telescope, which is designed to unravel the secrets of dark energy and dark matter, search for and image exoplanets, and explore many topics in infrared astrophysics. If successful, this would no doubt be one of the most groundbreaking scientific discoveries that may change our understanding of our existence and the universe as we know it.